A small animal lands on white Jurassic stone, and for a second it looks like a bird. Then it turns its head and the illusion breaks. There are teeth in its jaws. 3 clawed fingers jut from the wing. A long, bony tail drags a fan of feathers behind it. This is not the clean beginning of the modern world. This is the seam. 150 million years later, that body will become one of the most famous fossils ever found. It will arrive just after Darwin publishes On the Origin of Species. It will be called the first bird, then challenged, then reinterpreted again and again. And even now, in 2025 and 2026, new fossils and new scans are still changing the answer to the same question. Was Archaeopteryx really a bird? How well could it fly? And why did one dead animal become evidence in one of the biggest scientific arguments in history? Late Jurassic Bavaria did not look like the green Europe of today. Around 150 million years ago, this region sat in a warm tropical belt, broken into islands, carbonate flats, shallow lagoons, and reef barriers. The water could be brilliantly clear in one place and deadly still in another. White mud settled out of it in layers so fine they would one day preserve the outlines of wings. Between those lagoons, low islands held patches of vegetation, open ground, insects, small reptiles, and the daily traffic of life trying not to slip into the wrong basin. Somewhere on one of those islands, a feathered dinosaur moves through the heat. It is small, roughly in the range of a raven, magpie, or small chicken, depending on the specimen you compare it to. The head is light but not delicate. The jaws carry small teeth. The forelimbs bear long feathers arranged into wings, but the hand at the end is still unmistakably a grasping dinosaur hand. The tail is not a stub like a modern bird's. It is a full, bony rod, vertebra after vertebra, with feathers running along it like a banner built on bone. If you saw it in motion from a distance, you might think bird first. That reaction is understandable. The feathers are real. The wings are real. Some of the flight feathers are asymmetrical, the kind of design associated with aerodynamic control. But come closer and the categories begin to fail. Modern birds do not carry long reptilian tails. Modern birds do not keep 3 free clawed fingers on the wing. Modern birds do not bite with toothed jaws. Archaeopteryx feels familiar only until you actually look at it. That matters, because the easy version of this animal is wrong in both directions. It was not simply a modern bird waiting early, but it was not just a small ground predator wearing decorative feathers either. It occupied a narrower, stranger space. It lived close to the origin of birds, close enough that the usual labels blur. If modern birds are living dinosaurs, Archaeopteryx stood very near the part of the story where that sentence stops sounding metaphorical and becomes anatomy. Its world also shaped what kind of animal it could be. This was not a dense Cretaceous rainforest full of flowering canopies and familiar bird perches. Solnhofen was more fragmented and coastal. Open ground mattered. Rocks mattered. Lagoon margins mattered. Wind moving across exposed surfaces mattered. So when people argue over whether Archaeopteryx was tree-dwelling or ground-dwelling, they are often compressing a more complicated possibility into a false choice. The landscape itself suggests a creature that may have used several levels of its environment without owning any of them as perfectly as later birds would. Above it, pterosaurs cross the sky. Not dinosaurs, but flying reptiles on their own separate branch. Around it, fishes move through the lagoons, crustaceans crawl through shallows, dragonflies and other insects flash through the air, and small terrestrial animals search the islands for food and shelter. Archaeopteryx lives inside that traffic. It is not a symbol here. It is not a museum icon here. It is just another animal trying to launch before something larger arrives, or to land before momentum becomes injury. And that is the first thing worth recovering from all the mythology. Archaeopteryx did not know it was transitional. It did not know it sat near the dinosaur-bird boundary humans would later argue about. It only knew how to survive in a place where a few meters of air could matter, a few seconds of lift could matter, and a bad fall into the wrong water could end everything. The strange thing is that almost everything that makes this animal famous was discovered only after it was dead. Archaeopteryx owes its fame not just to what it was, but to where it died. The fossils come from the Solnhofen limestone, also called Solnhofen Plattenkalk, a fine-grained Jurassic limestone in Bavaria that was quarried for centuries. People did not go there looking for revolutionary bird-dinosaur fossils. They went there because the stone split into thin, smooth sheets useful for building and later for lithographic printing. Human industry cut into the archive by accident. The environmental trap behind that archive was unusually effective. Parts of the Solnhofen system seem to have been quiet marine basins isolated by reefs and islands. Fine carbonate mud settled slowly through still water. Oxygen was low. In some basins, salinity may also have been stressful. Scavengers were limited. Currents were weak. So a body that reached the bottom might lie undisturbed long enough for details that usually vanish first to leave a record. Membranes, skin, fish fins, insect wings, jellyfish outlines, and, in the most famous case, feathers. That does not mean preservation was magical. It means it was precise and cruel. An animal falls, or is blown, or is washed into water that is calm enough to keep its shape, but hostile enough to keep other life away. The body sinks. Soft tissue decays, but not before the surrounding mud records its boundary. Bones settle. Feather shafts leave chemical traces. Later sediments seal the scene. Then pressure, mineral change, and deep time turn a dead body into a slab that can be split open like a sentence waiting to be read. Solnhofen is one of those rare places where absence becomes evidence. The feathers on Archaeopteryx are usually not preserved as fluffy three-dimensional plumage. They survive as impressions, stains, shadows, chemical residues, and fine textures against pale stone. That is enough. In some fossils, it is more than enough. You do not need every molecule of a feather if the rock has remembered where the feather was, how it lay, and how it met the air. This is why Solnhofen mattered so much to science. Without preservation this good, Archaeopteryx might have been just another small theropod skeleton. The teeth would still have been there, the tail would still have been there, but the wings would have lost their force. The fossil would not have carried the same argument, because the argument was never only, here is a skeleton. It was, here is a skeleton with feathers. Even today, new methods keep extracting more from that stone. Synchrotron imaging has shown that some feather structures preserved chemical information rather than mere outline. CT scanning lets researchers see through unprepared or crushed areas. Ultraviolet light reveals tissues and textures invisible under ordinary viewing. The fossil did not stop changing because it was buried. It kept changing because the tools used to interrogate it kept improving. And there is another twist. Solnhofen did not preserve Archaeopteryx because anyone cared about evolution. It preserved Archaeopteryx because geology, chemistry, and chance aligned in a lagoon long before humans existed. Then quarrymen, cutting stone for practical reasons, stumbled into one of the most politically charged fossils in the history of science. By the time humans found it, the feathers were still there, not as feathers, but as shadows. Timing made Archaeopteryx explosive. Charles Darwin published On the Origin of Species on 24 November 1859. The book argued that species were not fixed creations, but products of descent with modification through natural selection. The idea did not appear in a vacuum, but Darwin gave it a structure, a mechanism, and a public force that reshaped biology. Almost immediately, critics asked the question that always haunts new evolutionary ideas: where are the transitional forms? Then, in 1861, a single fossil feather from the Solnhofen limestone was described. Around the same time, the first skeletal specimen came to light from the same region. This was an astonishing coincidence. Here was a feather from ancient Jurassic rock, followed by a skeleton that seemed to combine a bird's plumage with reptilian anatomy. If you had designed a fossil specifically to intensify the argument over evolution in the early 1860s, you would have designed something very close to Archaeopteryx. The first major skeleton, later known as the London specimen, was bought for the British Museum in 1862 from the collector Carl Haberlein. Richard Owen, the great anatomist who coined the word dinosauria and who was also a powerful critic of Darwin in key respects, described the fossil in 1863. Owen recognized its importance, but he approached it cautiously. He generally treated Archaeopteryx as a bird, even while describing a body that carried deeply reptilian features. That caution was not just scientific, it was cultural. Evolution was not yet a settled framework, it was a battleground. Archaeopteryx entered that battleground as evidence, but not as simple evidence. A fossil can be politically useful before it is anatomically understood. And in the 1860s, many parts of Archaeopteryx were still poorly known or missing. The first skeleton lacked much of the head. Some anatomical details were misread. The public saw a dramatic hybrid. Scientists saw a problem that would take generations to unpack. Thomas Henry Huxley pushed the argument further. In the late 1860s, he compared birds with small theropod dinosaurs, such as Compsognathus, and argued that the relationship between birds and reptiles was far closer than traditional classification allowed. Huxley did not have the full mountain of fossil evidence later paleontologists would inherit. He did not know about feathered dinosaurs from China. He did not know about modern CT imaging. But he recognized something essential. The line between birds and certain dinosaurs was thinner than most of his contemporaries wanted to admit. That is why Archaeopteryx became more than a fossil. It became a courtroom exhibit in a case science was still trying to define. Supporters of evolution could point to it and say, here is a body with feathers and teeth, wings and claws, avian impressions and reptilian architecture. Critics could reply that the mixture was being overstated, or that the creature was still simply a bird, or that the theory built around it reached too far. The same slab fed both conviction and resistance. For the public, Archaeopteryx quickly became iconic because it seemed to dramatize a phrase everyone could understand: missing link. Scientists use that phrase more carefully now because evolution is not a chain with one missing segment, but a branching history full of side paths and cousin lineages. Even so, the fossil's symbolic power was obvious. It seemed to make transition visible. It seemed to say that categories humans treated as separate had once bled into each other. And yet, the deeper irony is that Archaeopteryx did not simplify evolution, it complicated it. The fossil did not end the argument over what a bird is, it started a more difficult one. Because once you had a feathered animal with dinosaur bones and bird-like wings, the categories themselves had to be re-examined. Science had found a bridge, but it would spend the next 160 years arguing which side of the bridge Archaeopteryx stood on. Start with the skull, because the skull tells you immediately that Archaeopteryx is not a modern bird. The jaws carried small teeth, not serrated steak knives, not the heavy crushing dentition of larger theropods, but real teeth nonetheless. In life, they probably suited seizing small prey rather than tearing apart large carcasses. For a public raised on the image of birds as beaked animals, those teeth were one of the first signals that something old and unfamiliar was looking back out of the slab. Then the tail. Modern birds shorten and fuse the end of the tail into a pygostyle, a compact anchor for tail feathers. Archaeopteryx still carried the ancestral pattern, a long series of separate caudal vertebrae extending far behind the pelvis. It is one of the most visually dinosaurian parts of the body. But the tail was not just an archaic leftover. It also carried feathers, meaning the animal's rear end was still part of its aerodynamic and display anatomy, even before the modern bird tail evolved. Now the hands. Each wing ended in 3 separate fingers with claws. That is not a decorative detail. It means the forelimb of Archaeopteryx was still a grasping theropod forelimb, transformed by feathers, rather than a modern fused bird wing. The fingers retained mobility. Recent work on the Chicago specimen even suggests the minor digit remained free and mobile distally, challenging older interpretations that made the hand more bird-like than it really was. In other words, the wing was still carrying a very old hand inside it. But bird-like traits are everywhere too. Archaeopteryx had feathers with a clear aerodynamic organization. It had a furcula, the wishbone, part of the structural package associated with theropod ancestry and avian flight mechanics. Its bones were lightly built. The forelimbs were elongated. The shoulder region, though not modern, was moving toward the architecture required for aerial locomotion. You cannot reduce that body to reptile with feathers without discarding the most important transformations already in progress. This is where the old public phrase, half bird, half dinosaur, fails. It sounds vivid, but scientifically it distorts what evolution does. Evolution does not assemble creatures by cutting 2 finished animals in half and welding them together. It changes populations, trait by trait, function by function, over deep time. Some features shift early, some shift late, some shift for one purpose and later get recruited for another. What you get in forms like Archaeopteryx is not a chimera, it is a mosaic. That mosaic extended to the feet as well. The hallux, the first toe, appears more reversed than in many close non-avian relatives, which hints at some incipient grasping or perching ability. But the story does not end there. The Chicago specimen's foot pads and scales suggest a foot adapted strongly for terrestrial locomotion, rather than the highly specialized raptorial or branch-locking condition of many modern birds. So the feet do not hand us a simple tree percher. They hand us an animal that may have perched sometimes, grasped sometimes, but still spent substantial time moving on the ground. The same pattern appears in the chest and flight apparatus. Archaeopteryx did not possess the full suite of advanced modern bird adaptations. It lacked the deep-keeled sternum of powerful flyers. Its shoulder mechanics likely limited the exact form of its wing stroke. The body was close to the air, but not yet built like the specialized flying machines birds would later become. That is why calling it simply the first bird can hide the harder, more interesting truth. Birdness itself was still under construction. Recent work has also complicated the skull in important ways. The Chicago specimen revealed a palate that looks intermediate between non-avian paravavian theropods and more crownward birds. That matters because one of the long-term trends in bird evolution involves a less rigid skull and new forms of cranial movement. Archaeopteryx does not complete that process, but it shows that the skull, like the wing and foot, was already being remodeled. And once you accept that, the whole body reads differently. Feathers did not arrive all at once with every other avian feature. The tail did not disappear overnight. Teeth did not vanish before wings became useful. Modern birds did not burst into existence fully assembled. They emerged through staged, overlapping, sometimes messy changes in bodies like this one. And the most important part of the animal was also the most misunderstood: the wings. This is the question that has followed Archaeopteryx from the 19th century to the present. And the answer is no longer probably not or obviously yes. The best evidence now points somewhere more specific and more revealing. Archaeopteryx almost certainly had real aerodynamic capability, but it probably did not fly like a swallow, a crow, or a hawk. Its flight was likely limited, powerful in bursts, and tied to a body that still belonged partly to the ground. The feathers were the first clue. Some wing feathers in Archaeopteryx are asymmetrical, a feature associated in living birds with aerodynamic performance rather than simple insulation. That does not prove modern-style flight on its own, but it tells us the wing was not just ornamental. The structure of the plumage was doing work. And in 2014, a new specimen with extensive feather preservation showed that plumage complexity in Archaeopteryx extended across the body and legs as well, reinforcing the idea that feathers had functions beyond a single clean category. Then came the bone evidence. In 2018, a study in Nature Communications examined wing bone geometry in several Archaeopteryx specimens using phase contrast synchrotron microtomography. The researchers found that the architecture of the wing bones clustered not with fully terrestrial dinosaurs, but with volant birds, especially birds that use short-distance flapping. Their interpretation was that Archaeopteryx actively used wing flapping to take to the air, though with a flight stroke different from that of most living birds. That already moved the debate, but the Chicago specimen pushed it further in 2025. For the first time, researchers documented specialized tertial feathers on both wings. These inner secondary feathers help close the gap between the body and the rest of the wing, creating a more continuous aerodynamic surface. Their absence in close flightless feathered dinosaur relatives matters. It means Archaeopteryx was not merely carrying bird-like feathers, it was refining the actual airfoil in a way consistent with feather-driven flight. The effect of that discovery is easy to underestimate if you only hear the word tertials and tune out. But think about what it means in physical terms. A gap between body and wing disrupts smooth lift production. Close that gap, and the wing becomes a better surface for moving air. So the Chicago fossil did not just add another feather detail, it added evidence that parts of the wing were evolving specifically for flight performance. Even so, Archaeopteryx still falls short of modern birds in crucial ways. The shoulder anatomy probably constrained how high the wing could be raised. The sternum was not the deep modern anchor for massive flight muscles. The body retained a long tail and hand claws. This was a flyer, but a primitive one. The wing beat may have been more antero-dorsally to postero-ventrally oriented, than the largely dorsoventral stroke of many living birds. In plain language, it could flap, but not with the same mechanical sophistication or efficiency we see later. That is why the old debate between trees down and ground up has softened. For decades, people argued as if Archaeopteryx had to fit neatly into one origin story for flight. Did it climb and glide from trees, or run and launch from the ground? The 2026 Ecology Review suggests a broader picture. Archaeopteryx may have combined terrestrial movement, gliding, limited powered flight, and retained grasping or climbing abilities. It may have launched from elevated surfaces sometimes, from the ground other times, and landed with less grace than later birds on both. Its footpads suggest terrestrial competence. Its reversed helix hints at early perching ability. Its curved manual claws and mobile fingers suggest retained grasping that could have been exapted for climbing. The ecology paper goes further and presents Archaeopteryx as a generalist forager rather than a specialist of one narrow habitat layer. That matters because ecological generalists often survive by mixing behaviors instead of perfecting only one. So could Archaeopteryx fly? Yes, probably. But yes is only the beginning. It likely flew in short bursts. It likely depended on flapping more than earlier skeptics allowed. It probably did not migrate long distances, soar elegantly for hours, or wheel through the air like a swift. This was not the final form of avian flight. It was one of the earliest workable drafts. And that answer changes the meaning of the animal. If Archaeopteryx could really power itself into the air, even imperfectly, then the transition from terrestrial dinosaur to flying bird was already far along by the late Jurassic. Which raises the next, more difficult question. If feathers and some wing structures were already present before fully modern flight, what were those features doing in the first place? So Archaeopteryx could fly. But that answer creates a harder question. Why did feathers evolve before flight? For a long time, feathers seemed like the defining property of birds. Archaeopteryx appeared feathered. Therefore, it looked bird-like. Therefore, feathers seemed to belong to the bird story. Then the fossil record widened. Feathered dinosaurs began turning up outside the crown of birds, especially among Maniraptoran theropods. Suddenly, feathers were no longer the badge that made Archaeopteryx unique. They were older than Archaeopteryx, older than birds in the narrow sense, and older than fully modern flight. This changed the logic of the problem. If non-avian dinosaurs already had feathers, then feathers did not arise solely to solve the problem of flying. They may have first evolved for insulation, display, brooding, sensory functions, camouflage, signaling, or several roles at once across different lineages and life stages. Evolution does not wait to invent a structure only when its final use becomes obvious. It builds something useful in one context, and later that same structure can be recruited for another. Archaeopteryx sits inside that broader feather revolution. The 2014 Nature paper describing a new specimen with extensive feather preservation found not just wing and tail feathers, but body and leg feathers as well, including what have been called feathered trousers on the hind limbs. That pattern reinforces a major point. Pennaceous feathers were not born as neat, exclusive flight equipment. Their history was already more complicated before Archaeopteryx ever opened its wings. Compare Archaeopteryx with animals like Anchiornis, Xiaotingia, and Orornis. These Jurassic or near-Jurassic para-avians reveal how blurred the boundary became once more fossils entered the picture. They show combinations of feathers, elongated forelimbs, and skeletal traits that overlap with Archaeopteryx in important ways. Then compare it with Microraptor, a later but very different animal with aerodynamic surfaces on both forelimbs and hind limbs. The message is not that all these animals were the same. The message is that early avian evolution was experimenting.
Experiment is the right word because no single lineage had yet monopolized the sky. Different Paravian dinosaurs were trying different aerodynamic layouts, different body sizes, different locomotor blends. Some were probably gliders. Some may have managed various grades of powered flight. Some carried feathered surfaces that were useful but not fully optimized. Archaeopteryx was part of that wider laboratory, not a lone genius springing fully formed from the Jurassic. This is also where mosaic evolution becomes visible at the level of entire body plans. Feathers come before the modern bird tail. Wings come before the modern shoulder. Avian-like airfoils appear before the fully modern flight stroke. Bird-like skull changes begin before the loss of teeth. The pieces do not arrive in textbook order because there was no textbook order. There was only selective pressure acting on populations in changing environments. And that makes Archaeopteryx more important, not less. If feathers were already common in some close dinosaur relatives, Archaeopteryx matters because it helps show when feathers crossed a functional threshold. The wing feathers are not just present, they are arranged as part of a flight-capable surface. The Chicago tertials strengthen that conclusion. Archaeopteryx was not the first feather, and probably not the first feathered dinosaur to leave the ground, but it remains one of the clearest windows into the stage where feathers, skeleton, and locomotion were beginning to work together as a true avian package. The feather was older than the bird. The wing was older than flight. Evolution had been building pieces without revealing the final design. To understand why Archaeopteryx looked and behaved the way it did, you have to place it back into the Solnhofen archipelago and refuse the temptation to imagine a generic dinosaur forest. This was a coastal island world. Lagoon basins lay behind reefs. Carbonate mudflats baked under heat. Some islands probably supported conifers, cycads, shrubs, and low vegetation rather than dense towering woodland everywhere. Shorelines mattered because shorelines create edges, and edges create opportunity. That environment supported an unusual mix of life. Solnhofen is famous not only for Archaeopteryx, but for fishes, crustaceans, horseshoe crabs, insects, pterosaurs, marine invertebrates, and delicate, soft-bodied organisms. The fossil assemblage tells us this was a world where marine influence sat almost on top of terrestrial habit. A small feathered dinosaur could move over land and still live within reach of tidal, lagoonal, and beachside resources. The 2026 Ecology Review presents Archaeopteryx as a likely generalist. Direct stomach contents are not known, so caution matters here. But its size, tooth shape, rostral sensitivity, and locomotor anatomy are consistent with small, energy-rich foods. Insects are a strong possibility. Other small prey may also have been taken when available. The review also suggests an omnivorous generalist diet could fit a seasonal island environment where resources shift and specialization becomes risky. That ecological flexibility fits the body. A strict aerial hunter would probably need better flight. A strict arboreal percher would probably need more specialized feet. A strict terrestrial runner would not need this wing. Archaeopteryx instead looks like a compromise animal in a compromise world, which may be exactly why it worked.
It could forage on the ground, gain short aerial advantage when threatened or when moving between surfaces, and perhaps climb or grasp when the terrain demanded it.
There is a quiet brutality to that kind of ecology. Every ability is partial. Every advantage has limits. You can fly, but not far. You can perch, but not like a modern songbird. You can run, but you are carrying wings that are expensive to grow and maintain. You can grasp, but your hand is also part of an airfoil. Archaeopteryx was not built around perfection. It was built around enough.
And enough may have been exactly what late Jurassic selection demanded. A few meters of powered escape from a predator, a brief launch across open ground, a climb to a safer resting point, a quick descent from an elevated rock or trunk, a body that could exploit several routes through its habitat without mastering any single route the way later birds would. That is not failure. That is transition doing real ecological work. In that world, being almost a bird may have been enough. Not perfect flight, just enough flight to survive.
One of the most misleading things about Archaeopteryx is how often it is talked about as if it were a single specimen. It is not. The history of Archaeopteryx is spread across multiple fossils, each one incomplete in a different way, each one revealing details the others did not. The London specimen mattered because it made the animal famous. The Berlin specimen became one of the most beautiful and informative examples. The Thermopolis specimen transformed discussion of the foot and theropod traits. Later specimens added plumage, chronology, and anatomy. The Chicago specimen expanded the story again.
This is how paleontology often really works. Not by finding one perfect fossil that ends the problem, but by assembling a species from fragments scattered across decades. One specimen preserves the tail better, another preserves the skull better, another is more complete but crushed, another is incomplete but chemically informative. New finds do not merely add quantity, they change which questions can be asked.
The Thermopolis specimen, for example, became especially important in the 2000s because it preserved features that strengthened the link between Archaeopteryx and non-avian theropod dinosaurs. The 2010 synchrotron imaging study on that specimen showed that some feather and bone chemistry remained detectable, proving that the slab held more than shape alone. The 2018 Schaumhaupten specimen pushed the known record slightly older by representing the oldest Archaeopteryx specimen from the earliest Tithonian Painton formation. The 2014 11th specimen added broad body plumage and leg feathers. The pattern is cumulative, but never simple. Then came the Chicago Archaeopteryx, the nearly complete and uncrushed 14th specimen described in Nature in May 2025. It was acquired by the Field Museum in 2022 after decades in private hands, and preparation guided by micro-CT turned it into one of the most informative specimens yet studied. It preserved skull details, a longer tail than previously recognized, soft tissues, foot pad morphology, and, crucially, specialized tertial feathers that help clarify the origin of an aerodynamic wing body surface. The Chicago fossil also showed how preparation itself can be a scientific act rather than mere cleanup. Removing stone too aggressively would have erased subtle tissues. Preparing slowly, under magnification, and with imaging guidance, preserved structures that older methods might never have recognized. That is a sobering thought. Some secrets of Archaeopteryx existed in the stone all along. Humans simply lacked the patience or technology to see them. Technology has repeatedly reopened Archaeopteryx. X-rays, CT scanning, UV imaging, synchrotron chemical mapping, and digital reconstruction have all changed what researchers can recover from old slabs. The fossil itself did not become younger, but in another sense, it kept becoming new. The more tools science developed, the more the limestone stopped being a static object and started behaving like a dense archive that had not yet finished speaking. The fossil did not change, the tools did, and every new tool pulled another secret out of the stone. For generations, Archaeopteryx dominated the Jurassic bird story simply because almost nothing else occupied the same space with comparable clarity. It was the icon, the benchmark, the fossil everyone had to pass through. But that monopoly has weakened. In February 2025, a Nature paper described Bomminornis zenhensis from the late Jurassic of China, dated to roughly 149 to 148 million years ago. And immediately, the story around the origin of birds became more crowded.
Bomminornis matters because it is the oldest known short-tailed avialan. Instead of the long, bony tail seen in Archaeopteryx and many close relatives, it had a short tail ending in a pygostyle, a much more bird-like condition. At the same time, it still retained a primitive hand reminiscent of non-avian Maniraptoran dinosaurs. Its pectoral and pelvic girdles also looked surprisingly advanced, showing that some derived bird features were already present in the late Jurassic.
That combination is classic mosaic evolution. It tells us that early bird-line dinosaurs were not marching in a neat single-file sequence from primitive to advanced. Different features were appearing in different combinations, in different lineages. Some traits that look modern in one part of the skeleton could coexist with much older patterns elsewhere in the same body. The same logic that makes Archaeopteryx hard to classify also applies to Bomminornis, but in a different arrangement.
And the historical implication is enormous. For a long time, if you wanted to picture the Jurassic origin of birds, Archaeopteryx was almost the whole frame. Bomminornis implies that by the late Jurassic, early avialans may already have been more diverse than the traditional picture allowed. The origin of birds may reach deeper into the Jurassic than the classic textbook narrative suggested. Archaeopteryx is still crucial, but it is no longer safe to imagine it as the lone opening chapter. That does not make Archaeopteryx irrelevant. In some ways, it makes it more valuable. If early avian evolution was already radiating into multiple body plans by the late Jurassic, then Archaeopteryx becomes one surviving witness among several lost experiments. It preserves a long-tailed, claw-handed, flight-capable condition near the base of avianlan history with extraordinary detail. Bomminornis shows that another route was already underway. Together, they reveal a deeper, messier, richer opening to bird evolution. And that should change how we use famous fossils. The goal is not to dethrone one icon and replace it with another. The goal is to recover the lost diversity behind the icon. Archaeopteryx was never less important because new discoveries complicated it. It became more honest, more situated, more real. Archaeopteryx was no longer the whole story. It became something better, the clearest witness to a story we had barely begun to uncover.
By now, the easy labels have all failed. Archaeopteryx was not a modern bird in the familiar sense. It did not have a shortened pygostyle tail, a fully modern chest, or the cleanly specialized flight apparatus of later avians. But it was not merely a ground dinosaur with pretty feathers either. It had asymmetrical flight feathers, wing bone geometry consistent with active flapping, aerodynamic tertials, and a body already committed to the air in ways its close non-avian relatives were not.
What it shows, more clearly than almost any fossil, is that evolution is not a ladder. It is not a straight climb from reptile to bird, from crude to refined, from wrong to right. It is a branching process full of partial solutions, shifted functions, retained ancestries, and bodies assembled in pieces. Teeth can remain while wings improve. Clawed fingers can persist while aerodynamic surfaces become more sophisticated. Ground movement can remain important while powered flight begins. That is not contradiction. That is how transitions look when they are real. Archaeopteryx also shows why fossils matter beyond naming species. This animal became a public symbol because it arrived at exactly the historical moment when science needed visible evidence that categories change through time. But its importance did not end there. It kept mattering because each new generation of researchers could ask a new question of the same stone. Could it fly? How well? What did the foot do? How was the skull changing? What did the feathers reveal? What did the mouth suggest about feeding and metabolism? The fossil stayed relevant because it was never exhausted.
Recent work has sharpened that point. The Chicago specimen suggests a more refined wing surface, a more complex skull, and soft tissues that help place Archaeopteryx ecologically. The 2026 Ecology Review presents it not as a one-dimensional protobird, but as a generalist, using ground foraging, incipient powered flight, gliding, and perhaps climbing or grasping in combination. The 2025 paper on Bominornis reveals that by the late Jurassic, bird-line dinosaurs were already diversifying into multiple forms. And the 2025-2026 work on the feeding apparatus suggests that the rise of flight carried physiological demands that reshaped the mouth itself.
That last point deserves more attention than it usually gets. Flight is expensive. It raises the energetic stakes of being alive. A body entering the air does not just need better wings. It may also need better ways to find, manipulate, and process food quickly enough to support those costs. The recent study on the Archaeopteryx feeding apparatus argues that some avian-style features of the mouth, including evidence interpreted as a sensitive bill tip structure, oral papillae, and increased tongue mobility, may reflect exactly that pressure. Even here, near the origin of birds, the demands of flight may already have been rippling outward into systems that are not obviously about flight at all.
That is another reason Archaeopteryx refuses to stay simple. It is not just a fossil about feathers. It is not just a fossil about one dramatic leap into the sky. It is a fossil about coordination. Bones, feathers, skin, behavior, metabolism, and feeding all had to be renegotiated as one dinosaurian lineage became increasingly avian. Every new specimen exposes another part of that negotiation.
So what is Archaeopteryx really? The safest answer is also the most powerful one. It is a feathered dinosaur close to the origin of birds. It is one of the earliest known dinosaurs with strong evidence for feather-driven flight. It is not certainly the direct ancestor of modern birds, and it may represent a side branch near that origin rather than the line that led straight to living species. But it remains indispensable for understanding how the dinosaur-bird transition actually unfolded.
And that transition matters, because modern birds are not an exception to the age of dinosaurs. They are its survivors. Archaeopteryx lived almost 85 million years before the asteroid impact at the end of the Cretaceous. It never saw the final catastrophe that erased all non-avian dinosaurs. But the wider lineage it helps illuminate eventually led to the only dinosaurs still alive today: birds. Every sparrow, gull, raven, hawk, penguin, and pigeon carries that deep history in transformed form.
Return then to the living animal on a Jurassic island. Not the fossil, not the icon, the animal. It lands on pale stone. It scans the ground. It tracks a movement in the brush or at the shoreline. It may launch in a short burst, or climb, or hop, or run. Its wings are useful, but not yet elegant. Its tail is heavy, but still feathered. Its mouth still bites with teeth. It is not trying to become a bird. It is only trying to stay alive.
And maybe that is why Archaeopteryx still holds its power. It reminds us that evolutionary transitions are not abstract diagrams. They were lived. They happened inside ordinary days, in ordinary acts of feeding and escaping and landing badly and trying again. A body does not become historic while it is alive. It becomes historic because time later reveals what that body was connecting.
Archaeopteryx was not the moment dinosaurs ended and birds began. It was the moment we finally saw that the boundary had never been clean.